Remember that each membrane has different properties and therefore different advantages and disadvantages. Make sure you select the membrane that best suits your sample type, the concentration of your samples, and even the buffers that you intend to use. Some researchers prefer using PVDF membranes because of their higher binding capacity and chemical and physical resistance. Others prefer using nitrocellulose, which does not require methanol activation and is less expensive. Don't forget that despite the membrane type you choose to use, you should never exceed its binding capacity. PVDF membranes usually have a binding capacity between 150 and 160 micrograms per square centimeter, while nitrocellulose membranes have a binding capacity of approximately 80 micrograms per square centimeter. Remember that when it comes to Western blots, more is not always better, so you don't have to necessarily choose PVDF membranes just because they have a higher binding capacity. What you want to make sure is that you don't overload your gel and that you're always working within the linear range of your particular targets of interest. Remember that if you need more information on linear range calculation, we do have a Lambda U course on that topic, so please refer to that. Now, in reality, most targets will work just fine in both nitrocellulose or PVDF membranes. However, every now and then we will find a target that only works on PVDF or that only works on nitrocellulose. To avoid that type of situation, a quick literature search may help you determine what would be the best membrane for you. The best solution, however, is to always test both membranes during your pilot and optimization phase so you can choose the membrane that best suits your particular experimental conditions. PVDF membranes tend to have high autofluorescence, which can translate to high background, especially for near-infrared Western blotting. So when you're preparing near-infrared Western blots, you want to make sure that you use low fluorescence PVDF membranes. If you have membranes that you're not sure are going to work well with your detection chemistry, make sure you test them beforehand. The simplest way to do that is to image them without having any samples or antibodies on them. Get a sample of your test membrane and image it both dry and wet with either PBS or TBS. Compare those results to the membranes that you know work well with that particular detection chemistry and make sure there's no elevated background. The last topic that we have to cover regarding how to choose the best membrane to transfer your proteins onto is its pore size. Most membranes have 0.45 micron pores, and that is very well suited for proteins larger than 20 kilodaltons. If you're working with proteins that are smaller than that, you should be using membranes that have 0.22 micron pores. You may ask yourself, why not just use 0.22 micron membranes for everything since they retain all sizes of proteins? Well, because they retain so much protein, they also tend to have higher background, and they are also more expensive. That's why researchers tend to limit their use only when they're working with very small proteins. Well, if we think about it, we spend a lot of time optimizing Western blots, and it's even worse when we don't even see a band. In those situations, we tend to blame the antibody, our sample, how much protein we're loading, and all sorts of different things throughout our protocol, but we rarely think about the membrane we're using. Now you know that the membrane you choose to perform your transfer in may actually make or break your experiment.